Section 13.7, polyprotic acids. Polyprotic acid is just an acid that has more than one dissociable proton. So something like phosphoric acid, which is going to have 3, or carbonic acid, which would have 2. It just means there's more than one proton. Poly meaning more than one, and protic meaning protons. They're always going to dissociate into a stepwise manner, one proton at a time. So I've got this whole big PowerPoint where I go through and I talk about removing this approximation and looking at a more exact solution for what happens with the polyprotic acid. But this idea that it's a stepwise manner is really going to speed things up for us, and it's going to let us treat it as just a weak acid or as a conjugate weak base. And so we're not going to worry about like, well, I've got this polyprotic acid. Does it dissociate all 3 protons? Because for our polyprotic acids, typically Ka1 is going to be much bigger than Ka2, and that's going to be much bigger than Ka3. And that's because as the negative charge on the acid increases, it becomes more difficult to remove that positively charged proton. And so, yeah, you're going to get some fully deprotonated form, but it is something like 10,000 times less than what you would get out of just Ka1. All right, and we'll look and see what's going to happen if we start off here with Ka2, and which way are we going to go? Are we going to treat Ka2 as something acting like a base or something acting like an acid? All right, so here are some Kas for several common acids. Right, phosphoric acid, that's one of the ones that's in soda pop. Arsenic and arsenic acid, hopefully you don't have to deal with those. Those are quite deadly. Carbonic acid, that's the bubbly in soda. It's also part of what keeps your blood buffered to physiological pH. Sulfuric acid actually has 2 labile protons. That first Ka is so big it's practically infinite, and then the second one is still a strong weak acid. But one of the things you're going to notice is that each of these Kas, right, the Ka for taking off for the first proton is always bigger than it is for the second, which is always going to be bigger than it is for the third, and by several orders of magnitude, right? So if you look at vitamin C, ascorbic acid, its Ka1 is 7.9 times 10 to the minus 5. So not very strong acid to begin with. You take that first proton off, and now it's down to 1.6 times 10 to the minus 12 as the Ka value. So let's do a quick concept check. We want to calculate the equilibrium concentration of PO3 minus in a 1 molar solution of H3PO4. I'll walk through some of the math for that in a subsequent video, but for right now, it's going to be very small because it's the fully deprotonated form, and it's 3.6 times 10 to the minus 19. You're basically looking at taking this Ka3 and seeing what's going to happen with that. All right. Typical of most polyprotic acids is that the successive Ka values are going to be very different. So Ka1 over Ka2 is 1 times 10 to the 5th. So it's 5 orders of magnitude difference between 1 and 2. And the Ks between the second and third protons are separated by another 5 orders of magnitude. So that our relative acid strengths for H3PO4 is going to be much stronger than it is for the H2PO4 minus, and that's going to be much stronger than it is for the HPO4 2 minus. The first dissociation step makes the most important contribution to the H+. So let's do another quick example. We're going to calculate the pH of a 1 molar H2SO4 solution. Our major species in solution are going to be H+, HSO4-, and H2O, where the first 2 ions are produced are the first complete dissociation step of the H2SO4. So we're going to treat it as a strong acid first. Then we're going to calculate the equilibrium concentrations for the dissociation of the HSO4-, that's going to be using Ka2, which will show if the ion dissociates enough to produce a significant contribution to the concentration of H+. Right. So we're going to set up our ice table as follows. So we're going to look at the HSO4. So this is from the first deprotonated form. It's going to lose a proton to form H+ and SO4 2-. It's got a Ka of 1.2 times 10 to the minus 2. And our equilibrium expression is H+ times SO4- divided by HSO4. We set up our ice table. Now, in the beginning, we've got 1 molar HSO4 and 1 molar H+. And that's because we started off with 1 molar H2SO4, and it completely dissociates in the beginning into HSO4 minus and H+. And one of the things we're going to see here is that this showing up as part of our equilibrium is going to do two things. It's going to suppress the dissociation of our HSO4, right? So we've added in something up here. We're adding in some products, but what does Le Chatelier say? It's going to move to the left, right? So the amount of H plus and SO4 2 minus that we're going to generate from dissociating will decrease. And this is called the common ion effect. And it's basically Le Chatelier's principle saying, yeah, we got to move that to the left. It's also going to make our math a little bit easier, right? So we're going to set up our ice table. We've got our equilibrium concentrations. We're going to substitute them back in. So we know it's H plus over SO4 2 minus divided by HSO4. So we'll do 1 plus X times X and 0.1 minus X. Because that X is, we're going to assume that it's small. We're going to do 0.1 times X divided by 0.1. And so X is going to be 0.12 times 10 to the minus 2. It's 1%. The approximation is going to be valid according to our 5% rule. So note that our X is not equal to H+. Our H+ concentration is going to be that initial 0.1 molar plus X. So it's going to be 1 molar plus 1 times 10 to the 1.02 times 10 to the minus 2. So it's going to be 1.012 molar. And that's pretty darn close to 1 molar. Thus, the dissociation of HSO4 minus does not make a significant contribution to the concentration of H+. So pretty much all of your protons are coming from that first dissociation. And since you've got an H+ concentration of 1 molar, our pH is going to be 0, which is rather interesting, right? So ponder for a second. Can you have a minus log concentration?